Hello viewers, before you is Mr. Leonard Omondi Osumba, a chemistry teacher at Kadzonzo Girls Secondary School. Today we have a topic entitled Reaction Rates and Reversible Reactions. This is a topic that is tested in all three chemistry papers, but mainly it can be tested in chemistry paper 3, that is chemistry practical, and reaction rates. Now today, in this topic, there are several sections that are normally covered. The first section is the definition of reaction rate, graphical illustration of the reaction rate as a process. We have properties to be considered when measuring reaction rates. We have collision theory, activation energy. We have graphical illustration of collision theory and activation energy. Then we have factors affecting reaction rate, such as concentration of the reactants, temperature, catalyst, light, surface area, and pressure. Then we also have another section that is reversible reactions. Under reversible reactions, we look at various reactions which can be reversed. That is, forward and backward reactions can take place. Then we also have equilibrium as a subtopic under this topic, where we look at the state of balance when a reaction is taking place that can be achieved at a given point, especially for the reversible reactions. Then lastly, not last, but the next section is about factors affecting the equilibrium, which we shall cover later, and then we also look at the applications of equilibrium at industrial level. So to begin with is to define reaction rate. What is reaction rate? Reaction rate is the measure of the measure of how much of the products are formed, or how much of the reactants consumed per unit time. Now, you'll realize that some chemical reactions take very short time for them to come to an end. For example, in the reaction between sodium sulfate solution and lead 2 nitrate solution, there is normally formation of a white precipitate within a short time. And this formation of white precipitate is because the sulfate ion of sodium sulfate reacts with the lead 2 ions of the lead 2 nitrate to form lead 2 sulfate. This one is the one responsible for white precipitate. This reaction takes a very short time. While another reaction, such as rusting of iron, takes a longer time. It can even take like 3 days for rusting to take place. That is for iron to combine with oxygen and some moisture to form hydrated iron 3 oxide, which is actually the rust. So reactions vary in terms of the time they take to come to completion. Now, the graphical illustration for the reaction rate can be indicated by this graph, where the y-axis is the concentration of the reactants or the products, and then the x-axis is for the time. Now, during the reaction, you'll realize that the products, the reactants are being consumed, and therefore it means as the reaction progresses, the quantity of the reactants decrease. For instance, when you react sodium sulfate and lead to nitrate solution, you realize that with the time, the concentration of the sulfate ions and the concentration of the lead 2 ions will be used up in the process, and therefore with the time their quantities will tend to reduce. And so this one can be illustrated by the fall in the graph. Then on the same note, during the reaction, there is increased formation of the product. That is, the product keep on increasing with the time, and it can be illustrated by the rise in this curve. So this one can be used to illustrate what happens during the reaction process. Now we have some of the properties that you should look at during a chemical reaction. One thing we have to notice that during a chemical reaction, there's normally change in mass. Just like we have said, there is decrease in the quantity of the reactants, while there is increase in the quantity of the products. So this is one property that we look at. The second property is change in volume. This one is especially in a case whereby the reactants are maybe gases. In a case whereby maybe you are reacting magnesium ribbon with hydrochloric acid, you are reacting magnesium and hydrochloric acid to form magnesium chloride and hydrogen gas. As the reaction progresses, you expect a change in the volume of hydrogen gas, which can be collected using maybe gas jar. You'll realize as the time progresses, more and more hydrogen gas will be collected. So you look at change in volume. In this case, we look at change in volume of the product, that is hydrogen gas produced. Then the third one is intensity of the color. And this case is normally common where precipitation reactions occur. Just like we have said, when you react a solution containing lead 2 ions and a solution containing sulfate ions, you realize that as time progresses, there will be intensity in terms of change in the color. Lead 2 sulfate is a white precipitate. So what you expect is that as the reaction progresses, the intensity of the precipitate increases. So you can use the same, also the intensity of the color. And then another area we cover under reaction rate is collision theory and activation energy. So we have to define, first of all, what is collision theory, what does it state, and then what is activation energy. Collision theory. Now let us consider a case where we have the lead two ions reacting with sulfate ions to form lead two sulfate. So suppose this one is the reacting, this is the beaker. So let's use 0, this one, to denote the lead two ions, and then this one to denote this particle, to denote the sulfate ion. So assuming that this one is the mixture of the lead two ions and then we have the sulfate ion. Now, collision theory states that during a chemical reaction, the particles must collide. In this case, we consider the lead two ion as a particle and the sulfate ion as a particle. Now, the collision theory further states that not all collisions can lead to the reaction to form products. So, the collisions which do not form products, we call them unsuccessful collisions. While collisions of particles which result in the formation of products, we call it successful collision. So in this case, the lead two ion and sulfate ions can combine to form lead two sulfate. In this case, this reaction is considered successful reaction. So to summarize what collision theory states, it states that when reactants combine, they must collide. And for the collision to lead to formation of the products, then there has to be some minimum amount of energy for those particles to collide. And that one brings us to the concept of activation energy. Activation energy. Now, activation energy means that it states that the reacting particles need some minimum amount of energy to cause successful collision so that the particles can combine to form products. So is the minimum energy required by the reacting particles to collide, to cause successful collision to form products. It can be graphically illustrated as shown So this is energy in kilojoule. Then this is reaction path. Assuming that we have the So in this graph, we can see that we have reactants combining, and during that process they have to collide so that they can combine. But that collision requires some minimum energy. So that energy, we actually talk about the kinetic energy. So that minimum energy is illustrated by this part that is actually curved, so that there is formation of product C. And in this case, we can consider this. Lead 2 ions require some minimum energy. Sulfate ions also require some minimum energy to collide. So that we have that combination to form the product. So that is that. Then the next bit is factors affecting reaction rates. The first factor is concentration. Now, concentration simply means the amount of substance present in a given volume of a solution. And in this case, the concentration is normally expressed in terms of moles per liter or in grams per liter. We look at the concentration of the reactants and concentration of the product. Now, the question is this: how does concentration affect the rate of reaction? We say that increase in concentration increases the rate of reaction, while decrease in concentration decreases the rate of a reaction. The question is this: why is it that when the concentration of the reactants are increased, then the rate of reaction will increase? This is because when you increase the concentration of the reactants, then it means that the quantity of the reacting particles increase to occupy a given space, and that one increases the rate of collision. And so increased frequency of collision is what actually leads to increased rate of the reaction. So we say that this is due to increased number of reacting particles. In this case, the reacting particles can be atoms, molecules, or ions. Which lead to increased rate of successful collisions to form products. Let us take an example where you have two setups. Setup A, where you have a beaker containing 40 cubic centimeters of 2 molar hydrochloric acid plus 2 centimeter piece of magnesium ribbon. And then we have setup B, also is having 40 cubic centimeters, but now 1 molar hydrochloric acid plus 2 centimeter piece of magnesium ribbon. So assuming this is the magnesium ribbon. Now, one thing you have to realize that when I talk of 2 molar hydrochloric acid, I mean 2 moles of hydrochloric acid in 1 liter of a solution, but has a volume of 40 cubic centimeters. Then if I talk of 40 cubic centimeters of 1 molar hydrochloric acid, I simply mean we have 1 mole of hydrochloric acid in 1 liter of a solution. But in this case, we have only measured 40 cubic centimeters. So in setup A, the concentration of hydrochloric acid is 2 molar. 2 molar, while here is 1 molar. So in this case, there is decrease in concentration. So if at all you were to put 2 centimeter piece of magnesium ribbon, you dip it in a hydrochloric acid, which is 2 molar, then you start a stopwatch immediately. What you will realize is that it will take a shorter time for this piece of magnesium ribbon to be used up. While in this case, though we have the same volume, but the concentration is slightly lower. So when you start the stopwatch, then you let the reaction to progress, then you realize that this one will take longer time. The reason why in setup B it will take longer time is because we have lower concentration of the hydrochloric acid. And so, because of that, there is decreased rate of collision. But here there is higher rate of collision. And that is why in this case you expect it to take shorter time. So in short, when you increase concentration, let's say from 1 molar to 2 molar, you are actually increasing the rate of reaction. For your information, in reactions where the concentration of the reactant is higher, it takes shorter time for the reaction to come to completion. So that is how concentration affects the rate of reaction. Then the second factor is temperature. Now the question is this: how does temperature affect the rate of reaction? The answer is increase in temperature increases the rate of a chemical reaction, while decrease in temperature decreases the rate of a chemical reaction. The question is why? Why does increase in temperature increases the rate of a chemical reaction? This is because when you increase temperature, you increase the kinetic energy of the reacting particles. So that increased kinetic energy increases the rate or the frequency of the collision of the reacting particles, so that these particles can combine to form products. So you say this is because increase in temperature increases the kinetic energy. Kinetic energy. This one is a key term of the reacting particles to cause increased frequency of successful collisions to cause reaction, thus forming products. So let's take a case whereby just the same scenario, but now in this case we are going to consider the same concentration, because we are not varying the concentration. We have 1 molar, let's say we are using 1 molar HCl and also 1 molar HCl. The volume the same. The length of the magnesium ribbon we are using also the same. But now because temperature is a variable in this case, then let's say that we subject setup A, this solution, before dipping the magnesium ribbon. Let's say that we heat it, we heat this one, let's say up to 50 degrees Celsius. And then we put the 2 cubic centimeter piece of magnesium ribbon. Then allow the reaction to take place. During the reaction, we know that when magnesium reacts with hydrochloric acid, there is formation of hydrogen gas, and so you expect rapid effervescence. That is, more bubbles will be produced in this case. So let's say that the reaction stops at after 50 seconds. I'm giving an instance. Let's say it takes 50 seconds for the reaction to proceed. To come to an end. And then you, in a setup B, you don't subject it to heating. The solution, let's say, is at room temperature, assuming that the room temperature is 25 degrees Celsius. Then you just dip the magnesium ribbon into this solution. Then you allow the reaction to begin. You start a stopwatch and then the reaction begins. Now you realize that because the temperature is lower in this setup B, you expect it to take longer time. Let's say it might take, 100 seconds. And this one confirms that increase in temperature increases the rate of the reaction. So you have to bear in mind that the main effect of temperature is the increased kinetic energy. The energy which the reacting particles require to move so that they can collide, to combine, to form products. Now in practical setting, another example that can be used to illustrate temperature, other than the reaction between magnesium ribbon and hydrochloric acid, we can talk about the reaction between sodium thiosulfate, solution which has a formula of this one, reacting with hydrochloric acid. In a case where we use this one as an example to illustrate how temperature affects the reaction rate, then we can have two setups on the same note, where we are going to use 1 molar hydrochloric acid, 1 molar sodium thiosulfate. And then we heat the solution to, we have hydrochloric acid 50 cubic centimeters, 50 degrees Celsius, that is the temperature. And then we mix the two. Then we start a stopwatch immediately. Then we let the reaction to occur. Now, the property that we shall be using here to measure the reaction rate is the intensity of the precipitate of the sulfur. So, sodium thiosulfate normally reacts with hydrochloric acid to form a pale yellow precipitate. Pale yellow precipitate of sulfur. We call it colloidal sulfur. So the intensity of the precipitate will increase at a faster rate where the temperature of the solution is at 50 degrees. And it will take shorter time if at all you are to use across a piece of paper, let's say filter paper marked X, it will take shorter time for that cross to disappear due to the formation of the precipitate that will cover the cross. While in setup B, because the temperature is lower, it will take longer time for the cross X to disappear. That is, it will take longer time for the colloidal sulfur to be formed. So that one marks the end of part 1.
This is a city on a hill, a school with God's glory. Education is light, my Kadzonzo, the only bright, shining star in the nation. Highly favored, my Kadzonzo, highly favored by God, so we are.